Just a couple of words about myself and Milano Multiphysics. I've been working as a researcher a few years before moving to the company I founded with my colleagues in 2015. I mainly worked on multiphysics modeling. The last academia I was on was UC Berkeley, was doing a postdoc researcher. And the idea of our small company, I mean, apart from the founder, we have only 6 employees. So you can, I mean, we are slowly growing, but you can realize how small the company is. Well, the reason we exist, we believe, is that we can tackle most of the problem going a little bit beyond the standard engineering consultancy approach. And what we do is mainly working on multiphysics modeling for what concern advanced reactors, so from coupling of Monte Carlo neutronics and CFD up to fuel cycle and design optimization. At the same time, we leverage on the skills and knowledge of our colleagues and employees to also tackle complex problems in the energy sector at large. So mainly forecast of electricity markets and renewable energy. So I give you a little bit of introduction why we believed, why we made this move, and why we believe this is important. The way that nuclear reactors were developed was, well, you get an idea, you start from the concept, then you do the hard work of design and deployment, mainly by experiment. I take Oak Ridge as an example, but in most of the countries, there is something similar that happened in the 50s, 60s, and 70s up to the 80s. Well, you test the idea, you run the reactor, you see how it works, and you change the design. That was great, and we ended up mostly with light water reactor, at least for the large fraction of the nuclear reactor operating today. Well, today, of course, everything changed. So we have new concept, new goals of sustainability, safety, and unfortunately, in most cases, we are stuck with the codes from the 80s that are approved and accredited towards the regulatory framework. So in many cases, we end up that even today, we are unable to get new reactor out of the box, and we are stuck with the old reactors, not because of lack of ideas, but sometimes because the lack of modeling tools. So what we want to replace is this part. Bear with me, we don't think that experiments are wrong. Of course, that's the ultimate goal of everything. You want to test your models in a real demonstrating condition. But doing experiment is expensive and long nowadays. What we claim is that we can move from the standard paradigm of design by experiment to the design by simulation. That doesn't mean, once more, that we want to replace experiment with computer. Just we want to add a numerical modeling step before in the chain of reactor design. And to do that, you need the proper model. So that's our goal and what we have been working on. We mainly have customers in the molten salt reactor development stage. So that's what we love working on. Just a quick example of what I'm not unable to present full screen. I'm really sorry about that. Let me see. Oh, there you go. It shouldn't be that difficult. Sorry about that. That's one of the kind of analysis that we like to show as an example of what we do. So let's imagine this is a molten salt reactor that you have. Do you guys see my pointer?
Yes, we can.
Okay, that's great. Thank you very much. Let's imagine that in this molten salt reactor, this is taken from the European project, MSFR, and some following up, some of safer. Let's imagine we have an accidental insertion of uranium, enriched uranium. You have a mix of phenomena that happens. So the mixing of enriched fuel with the standard enrichment fuel, you have the transport, the numerical diffusion, and then at the end you are injecting reactivity in the core, which rises the power, heats up the salt, cause both an increase in Doppler and a thermal expansion, which increases leakage. And this safely brings back the reactivity and the power down. And then the oscillation you see is just the circulation time of this reactor, which has a very high power density, around 4 seconds. Well, this kind of analysis couldn't be done without proper tool. Of course, this tool then need to be verified, assessed, and ultimately validated against experimental data. But the kind of analysis that numerical multiphysics modeling can give you can act as a fast track to selecting which design is good and which one is not. What kind of modification of your design can improve the response to accident? What kind of modification can increase the neutron economy and having a better fuel evolution? All this kind of analysis can be nowadays performed with state-of-the-art tool, and that's what we like. I'm bringing you a funny example, which is not strictly related to a nuclear energy, but of course it starts from there. This is the TRIGA Mark II reactor. We have one 33 kilometers that direction. I'm sure most of you have seen one of these reactors during their studies or a similar reactor. The TRIGA reactor is quite common. Just let me know how many of you are familiar with this kind of reactor. Is a type of reactor you're familiar with? Okay, I will assume you are. Can you guys hear me correctly? Okay, great.
Yes.
That's good. That's great. So let's see what happens to this reactor when we inject a bunch of neutron in one side. This is the fission at the first and second generation. This is the fission at the third and second generation, and so on. So what you can see is in a critical reactor, in any critical reactor, wherever I inject neutrons, I end up pretty quickly in a bunch of generation to the fundamental shape, where the neutrons are distributed everywhere in the core and mostly peaked in the center. The number of neutron generation required to get to the fundamental eigenmode of the system is an intrinsic feature of the reactor. There's a lot of implication in the safety analysis of the system. And one standard parameter we use to see how much decoupled the reactor is the dominance ratio. That is the ratio between the fundamental eigenvalue and the first excited eigenvalue. That's what we usually use as a metric of how a decoupled system is, that then is related to how easily it can get in oscillation or in severe power distortion. It's a nice eigenvalue problem, and in Monte Carlo there are no straightforward way to calculate higher eigenmodes. Since the standard power iteration implementation in continuous energy Monte Carlo code, like MCMP, Serpent, or many other codes, by default just give you the fundamental eigenmode. So what we are trying to solve here is this eigenvalue problem. This is the fission source distribution. This is the fission kernel, and this is the eigenvalues of the system. What is a fission kernel? So basically, the fission kernel just tells you what is the probability that a neutron born in a specific place will give you a fission in another specific place. So let's take this example. If I have a neutron that was born in this cell, and then I count the number of neutrons ending up in this other cell as the next generation, this is an estimate that Monte Carlo can give me of the next fission probability, and what we call the element ij of the fission matrix. And the fission matrix is one of the possible approach with which we can calculate higher eigenmode. So this is a cross section of PWR, and you see there are a few hundred assemblies, and the power distribution is pretty much flat. We have higher enrichment at the periphery, lower enrichment at the center, so this evens out the leakage, and the fundamental eigenmode, like we like in most PWR, is pretty flat. But now with fission matrix, we can calculate higher eigenmodes. So we see that the next two excited eigenmodes represent an imbalance between one side and the other of the reactor. And this number is what we are mostly interested in. And this number is the dominance ratio. So basically, in very large cores, the dominance ratio critically approaches 1. Stop me if you have any question or any comment, please. And in this case, the eigenvalue ratio is 0.995. That means in this reactor, we require a large number of generations to converge to the fundamental mode. Do you have any comments on question, guys?
Nothing.
Great. I go ahead. And once we can do that, we can use this for all sort of safety analysis. We have adopted this coupled with CFD calculation to see how oscillation appears and are dumped in reactor. We developed, though, an extended method, which is just a generalization of the fission matrix. So instead of looking on just the neutrons born in a single cell and counting the neutrons producing a fission in another single cell, we can apply a generalization of the fission matrix approach, which is the Petrov-Galerkin approximation of the eigenvalue problem. So we just use a random basis function. So let's take, we have a subspace of distribution in the core, a trial subspace and a test subspace, and then we are able to get the projection of the fission kernel. Once again, the fission kernel is a very, very simple concept that is very hard to calculate. It is just the probability for a neutron born in the spatial coordinate R to produce a fission in the spatial coordinate R prime. This is a double differential distribution, and R, it's not one coordinate, it's the coordinate in the space of the reactor. And well, Monte Carlo can easily calculate one estimate of this, in the sense you can throw as many neutrons as you want in R and just looking at where they go. Same we did for the TRIGA reactor, seeing the propagation of the fission distribution. Well, once you have these, if you're able to project this fission kernel that your standard Serpent or other Monte Carlo code can produce on a spatial distribution, we use, for example, coupling with CFD code OpenFOAM, you can build a generalized eigenvalue problem whose solution are a good approximation of the original eigenvalue problem of your reactor, which has no discretization in a direct way. So once we solve and we project back, skipping the boring part, we move from random distribution to the real eigenvalue, higher eigenmodes of the system. And if we compare this against other approaches, we find that we have a good approximation for the first few eigenmodes. And now the fun part is, well, okay, we have a method that can help us taking the fission kernel, which is what keeps alive the neutronics analysis of nuclear reactor, which is just the probability for a neutron to create a fission from one place to another. But this method can be applied to any other transport kernel we have. In our works, we came to be asked to run analysis of the car sharing fission kernel. I don't know, guys, if in your city you have the same craziness about these new car sharing services. We have a few of them in Milan, 5 or 6, and you can just book a car with your phone, find it somewhere on the street, and take it and go wherever you want, mainly in the city, sometimes even outside. Since we had access to this data within a project, we were asked to analyze what information the distribution of trips along a city can give us on the expected electricity consumption. Well, for example, let's put it simple, if we see a lot of um, car movement the day before a bridge days, well, there is a large probabilities that the following day will be assumed as similar to an holiday for what is some type of electricity consumption. So there are all sort of data that can be extracted by this number of trips. The period we analyzed was, as you can imagine, in the past months, during the pandemic, and moving from period of more or less normality to periods of severe lockdown in which most of the car were used for essential workers to move around the city without using standard public transportation. So this is a highly dimensional problem, quite complex to analyze, but we know that there are main drivers to the different type of usage of the cars, and we wanted just to get rid of the noise and project the information along the main data direction. And we know that all the problem is described by one single transport kernel, which is at a given time in a given day, the probability distribution for one car to start from one point and conclude its trip in a second point. By definition, this is a critical system because unless there are changes, there are no car lost and no new car coming. At each generation, we start from n cars and we end up with n cars. It's a very large data set in the sense we have in the order of millions of trips. And so neutronics is the best way to go. So let me give you an example of what is a fission kernel and how it extremely similar to the transport of neutrons we have seen in the TRIGA reactor a few slides before. So this is just one representation. Well, if we start from here, the red point, I hope you can see that in the suburb of Milan, near Sesto San Giovanni. Well, the blue dots are Monte Carlo samples of where the car went. Out of the entire database we were analyzing, well, we take all the cars starting from this point and we see where they ended their trip. Well, you can see that the probability distribution is not smooth all over Milan. It, of course, privileges staying close to where you start. So most probably, no one starting from here will end up completely on the other side of the cities because you will have taken another transportation means, or just because, well, if you live here and work here, probably you will just move. So there is a strong bias on where you end up your trip compared to when you start. Well, let's go back to the TRIGA reactor. This is the first generation of neutrons producing fission after injecting a neutron in this fuel element. So those are the several fuel elements of the TRIGA reactor I'm sure you're familiar with. And of course, one neutron born here, ideally, well, in theory, could produce a fission everywhere. But due to the fact that exist higher eigenmodes, there is a larger probability of just stopping nearby. And then if we look at the second generation, the question we are asking is, if I start with a neutron here, and then I track one generation with its descendants, and then the following generation, I can see where neutron will go in the second generation after being injected in one specific place of the reactor or of the cities. This is just one convolution of the fission kernel with itself. So I start from R, I end up to any possible R prime, and then I apply to this probability distribution the fission kernel again, and I find R double prime, R second, which is the probability distribution for a neutron to produce a fission after two generations when it is injected in this fuel element. And here we can proceed up to the convergence. Well, the same thing happens to car sharing data. So let's say if I start from Sesto San Giovanni, that's the expected generation, the expected distribution of the first car distribution, a car generation. And this is the distribution and the second. Well, what does it mean, the second distribution, the second generation distribution? It means, well, if I sample all the possible destination, and then I take this as starting point and I apply the transport kernel once more, I will see where I end up in the map. And again, after two generations, you see on this specific plot, there is still a memory of where it was started. If we start and then if we go ahead and we see the third and fourth generation, or let's call it this, the 0th generation, the first, the second, and the third, sooner I converge to the final distribution, which represents the average probability distribution for a car to start or end trip in Milan, regardless of where it was start. And like in the TRIGA reactor, it takes 5 to 6 generations to convert. So just from this picture, you can see that the behavior between car sharing in Milan and the TRIGA reactor is incredibly similar. Well, we do not deal with a 1 meter diameter reactor. We have a several kilometer diameter cities, but the behavior of the fission kernel and the transport kernel are very similar. So the idea is, well, let's skip the boring math. It's to use the same approach that we derived for neutrons to find what are the fundamental eigenmodes of Milan. Well, then in the next step, we apply this looking at how the fundamental and the excited eigenmodes were changing during the time. We were able to define what type of electricity consumption days we were in. But that's another story. So, well, we can create the A and B matrix for the generalized eigenvalue problem. And then after orthogonalizing the problem, we end up with a solution that we can use to reconstruct the system. Well, this is the fundamental eigenmode. And the K effective is not, well, K effective. If it was a reactor, we are a K effective. The K effective is not exactly 1 because we are some cars that are removed from the street just due to maintenance or refueling or other problem. But the system really looks like a reactor. So this is the fundamental eigenmode, and you see it's more or less spread out in the city where you have some peak near the main train station, near some highly densely populated neighborhood, but that's more or less the distribution. Then if we move to higher eigenmodes, we see exactly the same pattern we have seen in the TRIGA reactor. And if we were analyzing this as a nuclear reactor, the dominance ratio of the transport kernel of this system is extremely close to a TRIGA reactor, which itself is a tightly coupled nuclear reactor. So in neutronics term, Milan is a relatively small city. So if we were to define what Milan is, well, it's not a large PWR. We are more in the range of a small, fast neutron reactor in which in a few generations we end up everywhere we want in the city. That was just a funny example on how we deal with adopting neutronics methodologies on our daily life, and I made my best to find an example beyond the standard neutronics application. Um, that's pretty much it. So we like data science. That's what we do as well. We often are challenged by finding new ways of using fancy data science to analyze nuclear reactors. This is just a reminder that the knowledge you already guys have can and is worth trying giving a shot the other way around. Sometimes a very complex data analysis problem can be simplified and dealt with the standard legacy neutron transport tools that were developed in the 50s or before. And that's it. It was just